Okay, number 1. When more and more draws are made from the box, the shape of the histogram of the draws will approach the shape of, uh, that's true. That's true. No, that's correct. Um, but the shape of the histogram will also approach the shape of the probability histogram, which will be normally distributed. Um, so they're both correct, yeah. Yep. So it could be normal curve, but what I meant to ask was the probability histogram, which will be normally distributed. Okay. 2, what is the formula for the expected value when draws are made from the box? The average of the box times the number of draws. Hey, how are you? Good. Number 3, what is the formula for the standard error? The SD of the box times the square root of the number of draws. Okay? And the really interesting fact about that is, as the expected value increases, the chance error also increases, but because the chance error is increasing at a slower rate, the percent error is going to 0. Right? So if we do 100 draws, we multiply the average of the box by 100, but we only multiply the SD by 10. So the chance error is increasing the more draws we make, but the SE increases at a slower rate, which means that the percent error is going to go towards 0. All right, number 4. When more draws are made, the percent error is expected to go down, closer to 0. 5. When more draws are made, the chance error is expected to go up. When can you use the shortcut for the standard deviation of the box? When the box only has 2 numbers. Bryn, are you reading and paying attention? Oh, okay. Okay, sorry. Number 7. When do we need to worry about the edges of the columns of a probability histogram? When there are a small number of draws. Now, how small? Yeah, it all depends. It depends on a lot of things. So, when in doubt, use the edges. Right? When in doubt, use the edges. Because if you have enough draws that the edges don't matter, then using the edges is still going to give you the right answer. It all depends on what's in the box, how big it is, how accurate you want to be. There are so many variables. And like I told you before, statistics is the study of the definite maybe. Meh. That's kind of how it goes. All right. Number 8. A computer is programmed to output a random number from 1 to 7 when a button is pushed. To play the game, you must put $1 on the table and push the button. If the computer gives an even number, you lose $1. If the computer chooses an odd number, you get the $1 back and you win an additional $1. So, we could say that the box is that. But that box, nope, don't erase. That's not it. That's not correct. Oh, okay. So that box will only allow me to play the game. I want to build a box that tells me how much I'm going to win or lose. So what's going to be in that box? 4 ones, because there are four odd numbers. Okay. And then 3 zeros, because... Oh, sorry. Yeah, it's got to be -1. Why does it have to be -1? Because you are losing $1. Okay. What is the average of the box? So we add up 4 ones, and we add up 3 -1s, and we add those together, and I get 1. And how many numbers are in the box? 7. So the average of the box is 1/7, or What does that mean? On average, you win 14 cents per game. Is this a good game to play? Yeah, the more you play, the more you win. And on average, you're expected to win 14 cents for every play. Now, can you win 14 cents? No, which is why small numbers from the box are kind of hard to calculate. They're not very accurate. Yeah, if we do a large number of draws, the amount we win will be roughly 14 cents per game, give or take whatever the SE is for that particular set. Okay, so that was B and C. Everybody catch that? D, is this game worth playing? Yeah, definitely, because we have a positive. We would expect to win more than we lose. What is the expected value in 100 draws? We times this by 100. Yep. So if we play 100 times, we're expected to get $14.28. Okay. What is the SD of the box? I can do the shortcut here. So 1 minus negative 1 is plus 1. That's big minus small times the square root of 4/7 times 3/7. Does everybody understand that? Big minus small times the square root. It's 1 minus negative 1. So 2 times the square root. Oh, that's not working. 2 times the square. Oh my goodness. I'll get it. Just wait. No, I won't. 2 times the square root of 3/7 times 4/7. So I get 0.989. What does the SD mean in this case? On average, the numbers in the box are 0.989 units away from 0.14. That's what the SD tells us. How did I know it was going to be essentially 1? They're about 1 apart. Now, we're a little bit heavy on the positive side, which is why the SD was not 1. And that's why the average was not 0. Okay. What is the SE when 100 draws are made? We're going to times this by the square root of 100, and I get 9.89. So, if you play the game 100 times, what's going to happen?
On average, you're expected to make $14.28,
Give or take $10. And how many people will be inside that window? 68%. Okay? So there is a chance, a pretty good chance actually, that you'll be outside of that range. Right? 1 in 3 people will be outside of that range. So this is the expected value, give or take the SE. So 14.28 plus 9.89, and then 14.28 minus 9.89. If a whole bunch of people played this game 100 times, 2/3 of them will earn between $4 and $24. How do you increase your chance? I mean, could you still lose in 100 draws? Yeah. How do you increase your chance of winning? You just keep playing. The more you play, the more likely you are to win. We're pretty close to guaranteed, but there's still that. I mean, $4 isn't a lot. But if we played 1,000 times, then it would be harder to get $0 or less. Okay. Nine. Suppose that 60% of all people who are eligible for jury duty in a large city are in favor of capital punishment. We are interested in how this fact might affect the composition of a jury in a murder trial. Suppose a jury of 12 is to be randomly selected from all who are eligible for jury duty in that city. Build a box model. Yes. So, what does 12 represent? The number of draws. 12 has nothing to do with what's in the box. We will be making 12 draws. What do we know about the box? So, do we have any idea how many people are in the box? We have no clue. All we know is that 60% of them favor capital punishment. So, let's say there's 100 people, just to make it easy. What would be in the box? 60 ones and 40 zeros. Okay? Now the next question says, is this the only box we have? No. We could say 6 ones and 4 zeros, or we could say 600 ones and 400 zeros, or the easiest one would be 3 ones and 2 zeros. All of those will give me the exact same results. It's just a lot easier when you use calculations with that bottom one. So we want to simplify the box as far as we possibly can. Does that make sense? Now, it doesn't matter which box you use, but the more items in the box, the harder it's going to be to calculate. Okay? So, let's use this one. C, what is the average of the box? It's going to be 3 divided by 5 is 0.6. Oh my goodness. I already knew that. Right?
I didn't even get that, but now I get it.
I knew it was going to be 60% because that's what was told to me. I was told the average of the box. Okay? All right. D, if 12 jurors are chosen at random, how many are expected to be in favor of capital punishment? So we times this by 12, and we get 7.2. Right? But we're going to say 7.2, but it's technically 7. Okay. What is the SD of the box? Can I use the shortcut? Yes. Now, in this case, it's really obvious why I want to use the bottom box. Because the fractions are so much smaller. So it's going to be 1 minus 0, that's big minus small, times the square root of 3/5 times 2/5. Instead of, 400 over 100 times 600 over 100. So that's 0.48. What does that mean? On average, the tickets in the box are 0.48 units away from 0.6. Okay. What is the SE for 12 draws? So 0.48 times the square root of 12. So now what do I know? You expect 7 people, give or take 1.5 people. So probably so we would probably say 7, give or take 2. But when you answer questions on a test, just use the decimals. Okay, just go ahead and use the decimals. Okay. What is the chance that none of the 12 jurors selected favor capital punishment? So here, I need a normal curve. My expected value is 7.2, and my SE is, 1.6 repeating, or 1.66, not repeating, sorry. So we want to find the chance that nobody favors capital punishment. So down here at 0, right? Do I need to worry about edges? Yes, because we only made 12 draws. So the widths of the columns are big compared to the width of the graph, of the whole histogram. So we need it. So we can't say 0. We're actually going to say 0.5, 0.5. Okay? So we want to know how big is this column. So from 0.5 to negative 0.5. What about the people that are further to the left than that? There aren't any, right? You can't be negative. There's no such thing. So, how far is this? Nope, 7.2 minus, or actually it's 0.5 minus, because it needs to be negative. 0.5 minus 7.2. Okay, that's the distance. I need to convert that into standard units by dividing by 1.66, and I get a z-score of negative 4. Now, just for fun, negative 0.5 minus 7.2 divided by 1.66. So I'm looking for the area between negative 4 and negative 4.6, which is going to be very, very small, essentially 0. Okay? Is there a possibility? Could you get no, 12 times? Yes, but it's extremely unlikely. So the z-score, value minus average, or in this case, value minus expected value, divided by the SE. Yeah, so it's the same formula that's written up there. SE, right. In this case, it's SE. It's expected value in SE. On the chart, it says average in SD. Okay, so Z is extremely unlikely. Oh, I divided by the wrong. I need to fix my answer. I divided by the wrong thing. So let me highlight that. Yeah. Okay. So G, would you be surprised if nobody was in favor of capital punishment? Yes, it could happen, but it's really unlikely. It's essentially 0. Okay. 10. Shaquille O'Neal has a lifetime stats of free throws at 53%. So what's in the box? 53 ones and 47 zeros. Why not negative 1? You don't lose points when you miss. You just don't gain points. Okay? What's the average of the box? 0.53. Right? It tells us the average of the box. Now, do we have to have 53 tickets? No, we could have more than that or less. I guess less would be hard to. You can't have less. That's the smallest number. But you could have 530 ones and 470 zeros. We want the smallest one possible. Can you build a different... Oh, no, wrong one. Sorry. In 10 tries, what is the chance that he makes none of the shots? So we have a lot of work to do to answer this one.
Wait, it makes exactly 7 of
B. We're on B. So we need to do 0.53 times 10, which is 5.3. That's the EV. If he shoots 10 times, he would expect to make 5.3 shots. Okay. And then the SD of the box is going to be 1 times the square root of 0.53 times 0.47. So the square root of 0.53 times 0.47 gives me 0.499. Okay, now what do I do? I need the SE, so 0.499 times the square root of 10, because he's only doing 10 shots, so I get 1.5. So, if Shaquille O'Neal takes 10 shots, he's expected to make 5.3 shots, give or take 1.5 shots, which doesn't make a whole lot of sense. But those numbers will allow us to calculate probabilities. Do I need to worry about edges? Definitely. How come? Because we have a small number of shots. So 5.3 is here. And what's the chance that he makes none of the shots? So I think I messed this up on the answer. It should be from 0.5 to negative 0.5, right? So 0.5 minus 5.3 divided by 1.578. So the right z-score is negative 3.04. And then the left one would be negative 0.5 minus 5.3. And then divide that by 1.578. And I get negative 3.67. Now I need to find the area. Yeah, I need to find the area between that. So let's do zoom recall. And let me get rid of my, get rid of my graphs. And then we'll shade norm from negative 3.67 up to negative 3.04. So that area is going to be 1/1000th. Is that what I had? 0.1%. Yep. Hey, I did it right. So what does that mean? If he shoots 10 foul shots 1,000 times, one of those times he'll miss all of them in a row. Right? He has a 1 in 1,000 chance of missing all 10. Okay. So C, what is the chance he makes exactly 7? How are we going to calculate exactly 7? So it's going to be this column right here from 6.5 to 7.5. So 6.5 minus 5.3, and we divide that by 1.578. Yeah, that's the expected value. So my first z-score is 0.76, and then 7.5 minus 5.3, and I divide that by the SE, 1.578, and my right z-score, the expected value is the average of the box times the number of draws. So 1.39. Now I just need to do shade norm between 0.76 and 1.39. Does everybody understand where those numbers came from? Maddie, where'd you get lost? So, do you understand why the middle is 5.3? And you understand 1.578 as the SE. Okay? So, we don't have very many draws, so we have to use the edges. And actually, even if you have a lot of draws, to find exactly 7, you have to use the edges. Otherwise, you're gonna plug 7 in twice and get the same z-score. So we want to find the z-score for this and the z-score for that. So I take 6.5 and I subtract 5.3. That tells me how far that is. But then I have to divide it by the SE, which will tell me the z-score. And the first z-score is 0.76. And now for the right side, I take the value I'm looking for, and I subtract the expected value, and I divide by the SE, and I get 1.39. So I'm going to scrap this curve, and I'm going to graph the normal curve from 0, and I'm going to find the area between 0.76 and 1.39. And that will be the same area as this. Why do we prefer using the standard curve? Could we do shade norm on the regular curve, on this 5.3 curve? You could, but you'd have to change your window every single time you did it. So changing it to the standard normal curve, and you'd also have to plug in the SE and the expected value every time. The standard normal curve is just 0 or 1. So yeah, we definitely like the standard curve. Yeah, it fits the chart too. So left bound 0.76, right bound 1.39, z-score. I have no idea. That's just the variable they used. So we end up with 14%. So if Shaquille O'Neal takes 10 foul shots in a game, 14% of the time he will make 7 of those shots. Okay? In 400 shots, how many is he expected to make? How would I find that? So I'm going to take the average of the box and multiply it by 400. 5.3 times 400. He's expected to make 2,120. Oh, sorry. I'm off by, so it should be 212. Yeah, he can't make more than he shoots. Yeah, it should be 0.53 times 400. Yeah. What? 212 is the right answer. Yeah. So give or take how many? Well, the SD of the box times the square root of the number of draws. So the square root of 400 is 20. So 0.499 times 20, give or take 10. We found an SE, but the more draws you make, the SE changes. Right. Which number? Yep. 0.499 is the SD of the box. That's the square root of 400. The SD only talks about the box. The SE tells you what you would how far off you are for a particular number of draws. Yeah. So in the box, the average of the box is 0.53. The SD of the box is 0.499. Okay? If we make 10 draws, then 10 shots, he is expected to make 5.3 shots, give or take 1.5 shots. But if he shoots 400 times, then he's expected to make 212 shots, give or take 10. So the expected value grows the more draws you make. The SE grows the more draws you make. It's not 1.5. It's 20 times this. Right. Yes. Right. The average of the box and the SD never change. But If you draw a different amount of times, you're going to get a unique expected value and a unique SE. So the SE is tailored to that many draws. And when the draws increase, the expected value increases exactly like you would expect, but the SE grows slower. So as the number of draws, as the expected value grows, the SE grows, but not as fast as the expected value, which is why, right. So this one jumped a lot. And let's actually do 10,000 draws. In 10,000 shots, how many is expected to make? 5,300 by 0.53. But 0.499 times the square root of 10,000, which is 100, so you get 50. So see how much this grew from here to here? It grew 1,000 times larger. But this grew much slower. The percent error gets smaller. So as your draws increase, your expected value increases and your SE increases. But the SE increases at a slower rate, which is why your probability approaches 0. Okay. So, yeah. All right. So, we're now going to say, in 400 shots, what is the chance of making more than half? Is he expected to make more than half? Yeah, he's expected to make 43%. So, or 53%. So, in 400 draws, the expected value is 212. And I want the area to the right. Do I need to count edges? No, 400 is pretty big. I mean, we might be like 0.1% off. So it's 400 is large enough in this case, it's probably not going to matter. So we want to know the z-score from 200 to the right. Well, how far is 200? Yeah, more than half. So the middle is 212. But, right. So we want 50% or more. I shaded it wrong when I started, so that's probably what confused you. So 212 is right there. But I want to know what's the chance he makes half of 400 is 200. So 200 is right here, that area. How far are we from the expected value? 12 in terms of the SE would be 12 divided by 9.98. We're just going to say 10. 1.2. What does that mean? Oh, yeah, it should actually be negative 1.2. Well, how do I know it's negative? Because I'm on the left. So 200 minus 212 is negative 12. Divide by the SE, which is 10, or 0.98, gives me negative 1.2. That's the z-score. So I want the area from negative 1.2 to 5. So negative 1.2 up to 5. Now it should be higher than 50%, right? 88%. Well, we're doing 400 shots. This is, so let's say we broke Shaquille O'Neal's free throw records. 350, no, this, no, that doesn't work. So if we lined up every foul shot he took, and we took the first 400, and then the second 400, and we kept doing that, 88% of those groups would be larger than 200. Right? This doesn't mean 88% of his shots. It means 88% of the time he will take 400 shots and get 200 or more. Well, but if you broke his whole career into groups of 400. Okay. So F, in 10,000 shots, what is his chance of making more than half? So my new EV is 0.53 times 10,000, which is 5,300. My SE is going to be 0.499 times the square root of that, which is 49.9. What does that mean? He's expected to make 5,300 shots, give or take 49.9. Okay, so now we do this, 5,300. What value am I looking for? 5,000 or bigger. I want this area. So how far away am I? I am negative 300 away, and I'm going to divide that by 49.9, and I get a z-score of negative 6.
So,
100%. Now, is it actually 100%? No.
anything past -5.
Right. Anything below negative 5 or 5 is not really measurable. So we're less than 1% of 1%. Okay, so now that was the same sort of situation. If he was to do 400 shots in a row, he has an 88% chance of making more than half. But if he makes 10,000 shots, he's virtually guaranteed to make more than half. Okay? Yeah. Well, but we have trusted the 53% rule. That, you know, he shoots 53% regardless of anything else. Right. Ideal world, yep. Okay, number 11. Number 11, in one play of a game, a nickel, diamond, quarter are tossed. Listen up. What are you doing? If all three comes up heads, then you win $15. Otherwise, you lose 3. What does the box look like? Nope. What could happen? So, quarter, dime, nickel. What could happen? Head, head, head. In which case, you win $15. What else could happen? Head, tail, head, tail, head, 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 tail. That takes care of all of the single T's. What about the double T's? T, T, H, T, H, T, H, T, T, and T, T, T. So all of these contain a -3. So I have one copy of 15 and 1, 2, 3, 4, 5, 6, 7 copies of -3. 1, 2, 3, 4, 5, 6, 7. Okay? Now wait a minute. There's a much easier way to do this. How many options does the quarter have? The quarter, 2. How about the dime? What about the nickel? So how many possibilities are there? 2 times 2 times 2 is 8. How many of them are HHH? 1 out of 8. Okay? Now, just looking at the box, is this a good game to play? No, why not?
You lose seven out of 8 times.
Well, that doesn't matter. It's the dollar values that matter. If you play 8 times, how much will you win? Once, $15, and you'll lose 7 times. 3 times 7, 21. So you're expected to lose $6 if you play 8 times. So the average of the box is 15 minus 21 over 8. So the average of the box is 0.75. What does 0.75 negative? Thank you. Negative 0.75. What does that mean? 75 cents a game. Is this better or worse than roulette? Much worse. Roulette, you're only expected to lose 5 cents per game. So this is not a good game to play. So if you play once, listen up. If you play one time, what's the chance that you win? 1 in 8. If you play 8 times, you'd expect to win once. Okay? So, what is the probability of getting 3 heads in one play of the game? 1/8. There's only one way to win and 7 ways to lose. Okay? Find an appropriate box model. We have that. 1 ticket with 15 and 7 tickets of -3. How much would you expect to win in 100 plays? Lose $75. Ooh, that's a bad game to play. Okay. In roulette, it was only $5.20. Okay. How many people who play this game will lose $60 or more? So we draw. We're expected to lose -75. And we want to find the area where? Left of -60. Where is -60? To the right. So this is -60. Okay? So it's everything to the left. Now, do I need to worry about edges? There are 8 things in the box, and we're making 100 draws. This is kind of no man's land. If it was 500, I would say no. But with 100, let's do it just in case. Because there are 8 tickets in the box. So that's kind of a small number. I wonder what I did. I probably didn't put the... What number are we on? Oh, look at number 11. So with 100 draws, 59.9 if you worry about the endpoints, and 60% if you don't. So does it matter? Not really. This is kind of the edge of big numbers. But remember, every situation is different, because the number of draws and the numbers in the box and how many numbers are in the box, that all comes into the effect. So I need the SE. How do I find the SD? 15 plus 3 times the square root of 1/8 times 7/8. Does everybody understand that? Yep. So 18 times the square root of 1/8 divided by 7/8. Actually, it should be time 1/8 times 7/8. No, it doesn't matter. Multiplication commutes, so it doesn't matter. Okay, 5.9.
So how do you know it's divided by the SD or the SE?
Well, so when you're using a box model with a different number of draws, it's always SE. SD is if you are just looking at a column of data. How does this data compare to itself? That
Like this stuff, we're probably never going to use SD.
no. No, just like when we were doing regression, we never use the SD. We use the root mean squared. All right, so now I need to multiply that by the square root of 100. So times it by 10. So we are expected to lose $75, give or take $60. Could you win in 100 draws? Yeah, you could. So it's not very likely, but you could. So how far is it from here to here? $15. Positive or negative? We're going to the right, so it's positive. 15 divided by 59.52. Are we going right or are we going left? Right. So where is negative 60 compared to negative 75? It's 15 units to the right. So my z-score is positive 0.25. And I want to find the area between negative 5 and positive 0.25. So clear out my draws. And then we'll do shade norm from negative infinity to 0.25. So if a whole bunch of people play this game 100 times, 59.9% of them will lose $60 or more. So more than half of the people will lose $60 or more. Yeah, casino makes a lot of money. C, it's 100 times negative 0.75. Right, which means you lose. No, you just win a negative. B is the box. Okay, number 12. A gambler is going to play roulette 25 times, putting $1 on a split each time. So they're going to bet on 11 and 12 at the same time. If either number comes up, the gambler gets the dollar back and $17. A split pays 17 to 1. So what's in the box? 2 copies of 17 and 36 copies of negative 1. Right? Average of the box?
But don't you win 17 and your dollar?
No, you get it back. So you get your dollar back and then they pay you $17. So so it's like not even, the box is just saying if you lose you pay them $1. If you win they pay you 17. Yeah, so technically you don't need to put your dollar on the table as long as you agree to pay if you lose. So the average of the box is 34 minus 36 over 38. So 2 copies of 17 makes $34. 36 copies of negative 1 makes negative $36. So that's negative 2 over 38, which we already know is negative 0.052. Okay. Every game in roulette has a 5.2 cents disadvantage, except for the house special. Yeah, the house special was like 7 cents, 7.8 or something like that. Okay. We have the box model. What's the chance that the casino will win more than $2 in 25 plays? Do I need edges? Yes. So in 25 plays, negative 0.052 times 25, the expected value is negative 1.3. Right? Did I type that in right? Okay. So we want to know from negative 2 and down. Right? Do we need to worry about the edges? Yes, because this is small, so it's actually going to be, we're going to calculate negative 2.5. Okay, so negative 2.5 plus 1.3 gives me negative 1.2, so I need to convert that into standard units. Well, I don't have a z-score yet, or I don't have an SE yet. Average of the box, 2 plus 1 times the square root of 238 times 1, or 3638. Oh, it's not 2. It's 17. Thank you. Okay. 18 times the square root. Which 2? No, there's 2 of them. 36 copies of 38. So 2 divided by 38 times 3 divided by, or not 3, 36 divided by 38. So the SD of the box is 4. We're going to multiply that by the square root of 25. And my SE is 20. So we're expected to lose $1.30, give or take $20. So your chances are actually are not terribly bad with 25 draws. So we found our distance as negative 1.2. I need to divide that by 20. And I get a z-score of, no, that's not right. Sorry, negative 1.2 divided by 20. I did it backwards. 0.06. Okay, so I need to find the area between negative infinity and negative 0.06, which is probably going to be really close to 50%. So shade norm from negative infinity to negative 0.06. Oh, I didn't clear my draw, but 47.6%. Okay. 13. The Heart Association claims that only 10% of adults over 30 years of age in the country can pass the minimum fitness requirements for the Presidential Physical Fitness Commission. Suppose that 100 adults over 30 years of age are randomly selected and all are given the fitness test. So what's in the box? What is one possibility for the box? One copy of 1 and 9 copies of 0. Is that the only possibility? No, that's just the easiest. You could do 10 and 90 or 100 and 900. Okay, so average of the box is easy. 0.1. Okay, so if we choose 100 people, then the EV is going to be 0.1 times 100, which is 10. We would expect 10 people out of 100 to pass. I probably would not be one of them because I'm not flexible. I would like to say it's years since I touched my toes, but I'm never sure I've actually made it that far. You don't remember did you not do that in elementary? There were stretching exercises and I think jumping jacks and I can't remember, push-ups maybe.
I know how to make this content. Okay, stand up and spin around and then try again. No.
Ouch. Nope. I'm gonna get dizzy.
No, really, you'll be able to touch it.
Okay. So we need the SE. The SD of the box is going to be 1 minus 0 times 0.1 times 0.9. So the square root of 0.1 times 0.9. The SD of the box is 0.3. For 100 draws, so for 100 draws, I multiply by the square root of 100, which is 10. So times that by 10, 3. So the answer is 10, give or take 3. Find the probability that at least 16% of them will pass the minimum fitness requirements. So, how many people would 16% be? 16 people. So I'm expected to get 10, but I want 16 or more, which is 2 SDs, right? 3 plus 3 is 6, 2 SDs. How about edges? Yeah, probably not terribly important. So we know that the middle of 2, a z-score of 2 gives 95%. So how much is in the right tail? 2.5%. So without endpoints, we ended up with 2.5. Let's see what happens if we do use endpoints. So that would be 15.5, right? So that's 5.5 divided by 3. 5.5 divided by 3 is 1.83. So I want to find my z-score. Oops, that's not what I wanted. Z-score from 1.8333 up until, oh, I got that backwards. 1.83 until 5. So in this case, we end up with a right tail of 3.3%. Were endpoints important? Yes, but in the last problem, were endpoints important? No, but it was the same number of draws, right? We made 100 draws in both cases. So if it's somewhere in the middle, I would use endpoints. If it's, 400 or 1,000 or 10,000. We use the edge instead of just saying it was 95%. Yeah. Okay. Okay. I haven't asked you to do homework much, but will you please finish this page tonight? Just this page? That's the end, isn't it? No, there's 2 more pages. We have 3 more problems. So, yeah, just do 14, 15, and 16. 16's easy. 16 you just choose 1 or 2 each time. So do 14 through 16 and we'll finish it tomorrow.